Our goal is to explain and use the relationship between sine and cosine of complementary angles. So to start off, we're going to start with these two special right triangles. One of these we looked at recently in deriving the special right triangle theorem for this particular triangle, the 30, 60, 90. This is another one that is a special right triangle that has its own theorem, the 45, 45, 90. So the first thing I want to do is review what a complementary angle is. A complementary angle is a set of angles that add together to give us 90 degrees. So in this triangle here, we have 30 degrees plus 60 degrees equals 90 degrees. So 30 and 60 are complementary angles. In this triangle, I have 45 degrees plus 45 degrees equals 90 degrees. So these are the complementary angles. And then these are just right angles. So the focus of our discussion today is going to involve these acute angles here. They're complementary within the triangle, adding up to 90 degrees. Let's talk about the sine and the cosine. So this is a newer concept in this series, and it is a function. So that's one thing we should note. So using function notations, we would write this sine of x equals y, or cosine of x equals y. I subscripted these y sub 1 and y sub 2 because we don't have a guarantee that for any x that I put into here, it's going to be the same y as any y that I get out of this when I put the same x into here. What we want to do, though, is we want to look at a special situation today of the relationship between the sine and the cosine. And one little kind of historical note that I want to give you is that the co-part of cosine means complement of sine. So we are looking at the sine and the complement of sine. And the first one that I want to look at is this triangle here because it has some variety that this one doesn't have. Since the two complementary angles here are both 45, this isn't quite as interesting to look at as having two different angles to look at. So the first thing I want to do is I want to look at the sine of 30 degrees. And each sine, cosine, tangent, cosecant, the different trig functions that we have that we typically talk about in high school, those all are ratios of sides that are in relationship to each other. So the function relates an angle, which is the input here for the x, and the output is a ratio of sides. So that's an interesting note. So how does this work? In particular, the first thing I'm going to look at is the sine of 60 degrees. So my input for the x is going to be the 60 degrees. And then I'm going to have that in ratio to some sides. In sine, that means that I have the opposite side, and that's opposite the angle. So looking, if you observe from here, you're looking from here, the opposite side is the square root of 3 side. And that's going to be in relationship to the hypotenuse. The hypotenuse is always directly across from the 90-degree angle. So a little note we can put in there is the opposite over the hypotenuse. So I've labeled those in there. So I want the square root of 3 over 2. And if you've worked with trig before, you might recognize this is a value that you've been told you had to memorize. All right, so now what do I want to look at? I want to look at the cosine of 60 degrees now. And the cosine of 60 degrees is the adjacent over the hypotenuse. So this numerator is the thing that's changing in this. And so if I'm standing here and I'm looking, I've already labeled the opposite and the hypotenuse here. So the adjacent is the only side left in the triangle that we haven't labeled yet. Observe that the hypotenuse is also directly beside the angle as well, and that is true. But the hypotenuse in trig is always the hypotenuse. It's never going to take on a different label. So it's always the one that's directly across from the 90-degree angle. So while there's two sides directly beside the angle we're interested in, one of them is always going to be named hypotenuse. The other one is going to be the adjacent. All right, so looking at this ratio, the adjacent is 1, and the hypotenuse is still 2. So the cosine of 60 degrees is a half. And all right, now I want to switch my perspective. I want to look at my other angle, my complementary angle. I want to look at the sine of 30 degrees, and I want to look at the cosine of 30 degrees. And for this, we're going to have to change these labels. Since my perspective changes, my labels have to change. Okay, so what change happened? Well, since my perspective is here now, it's as if I'm standing in this corner looking out. So directly opposite from me is going to be this side. And directly beside me is going to be this side. So this is my adjacent side, this is my opposite side. Hypotenuse is the only thing that didn't change. It is still directly across from the 90-degree angle. So now, if I want to look at the sine of 30 degrees, remember that's the opposite over the hypotenuse. So now my opposite is 1 and my hypotenuse is 2. So we're going to have the sine of 30 degrees is a half. And then looking at my cosine, I had adjacent over hypotenuse here. So the adjacent is the one right beside it. So I have the square root of 3. And then the hypotenuse is still 2. So I have the square root of 3 over 2. And now let's look at what we have in this chart here. The sine of 60 degrees was square root of 3 half. The sine of 30 degrees is 1 half. When we look at the cosine of 60, we had a half here, and the cosine of 30 was square root of 3 over 2. So, looking at the sine of 60 and the sine of 30, we have these two values, and then looking at the sine of 60 and the sine of 30, those values are swapped. So that's an important feature here. The sine of 60 and the cosine of 30 have the same values. Remember what I said earlier, that the co part of cosine meant the complement of sine. Look what we have as the x value here, 60, and the x value here is 30. 60 and 30 are complementary angles, and cosine is the complement of sine. So the complements give us an equivalent y value. If I put in the 60 here, I get this value. If I put in its complement into the complement sign, I get the same value. So this is a special condition where we get the same y output. And then the same going the other way with the cosine of 60 degrees and the sine of 30 degrees. We start with sine of 30 degrees, we get a half. Do the complement of 30 is 60. The complement of sine will then give us the same half. All right, so that's using this triangle. So let's look at the one that I said wasn't quite as interesting. We have 45 degrees here. So if I put in the sine of 45 degrees, looking at this triangle, we still have these same ratios of opposite over hypotenuse. So the let's just choose this bottom right hand as our reference point. The opposite of this is going to be 1. And then the hypotenuse is the square root of 2. So the opposite is 1, and then the hypotenuse is the square root of 2. If I do the cosine of 45 degrees, what do we expect? This is the complement of this angle, and this is the complementary sine of this. If it follows the same pattern as before, then these should be the same value. Let's take a look. Using the same angle again as reference, the adjacent is 1. The hypotenuse is the square root of 2. So the adjacent over the hypotenuse is 1 over square root of 2. And so this held All right, so let's look at problem solving. I have another triangle down here. I have this side labeled, this angle labeled, this side labeled, and this angle labeled, and I have an unknown L. With all the information we have at this point, we have a couple different ways we could solve for this L. Since it's a right triangle, we could throw this into the Pythagorean theorem and solve for it. So that's one method to do this. Another method to do this would be to use some of our newfound trig knowledge. And so we should be able to plug some values into this and solve for it. So there's two different ways to do this. What I want to do is I want to use some of our new trig ideas to reinforce how to solve for this. So right now we're going to take a second. You can pause the video, see if you can solve for L. All right, so we're going to look at solving for L. So I know the adjacent side and I know the hypotenuse. Looking back at here, the one that involved the adjacent and the hypotenuse is the cosine, so that's the function I'm going to use. Also notice that I know a side, an angle, and a side in that order. So I have side, angle, side congruence. That is important to understand that we definitely have a congruence that we can establish. If we should have something like side-side angle, where we didn't know this angle for sure, but we knew this side, and this angle, then we could not guarantee a congruence and could not definitively solve this problem. So it's important to remember those congruence things that you've studied earlier in the year. So how can we solve for this unknown? Well, just like we've put together this information with this triangle, we're going to try to put one of these trig ideas together so that it contains an unknown. And for that, we're going to use the complement operation here, the sine. The sine of 60 degrees is going to be the opposite over the hypotenuse. Opposite of 60 is L, and then the hypotenuse is 2.1. So in this one, this should be true also. And we don't know what this L is, and that unknown is there. So one thing you might... So what we are going to use is some proportionalities. Notice we have a 90 and a 60 here, so we know that this missing angle by the triangle angle sum theorem should be 30, which means that this orange triangle down here and this brown triangle up here are similar triangles. They have the same angle measures, those are all congruent, and so these sides should be in proportion to each other based on an earlier theorem. So we can set up a proportionality. We already looked at setting up a sine of 60 degrees here. We have that one right here. So the sine of 60 degrees was square root of 3 over 2 here, so that should be in proportion to this thing here because these are similar triangles. So we're going to set this equal to the square root of 3 over 2. And now we're going to ignore this piece over here and look at just this and solve this through our normal proportionality solving techniques. For this, I'm going to cross multiply and then divide. So L times 2 is going to be 2L, and then 2.1 times square root of 3 is 2.1 square root 3.